Okay, good. Can you all see this then?
Yes.
Okay, good. Yeah, I thought I would talk about quantum machine learning because I know that there are several other talks about quantum machine learning in the workshop. And the main reason for talking about quantum machine learning is that if you look at the field of quantum computation, which is a very exciting field and going really great right now with all kinds of advances, one of the main problems or issues is what if you can build a large-scale quantum computer, what do you do with it? And so there are, of course, famous algorithms like factoring, Shor's algorithm. But the problem with factoring is that it's not really a killer app for quantum computers. It's more like a suicide app in the sense that if you can implement it, then people will not use RSA public cryptography again. And then, of course, there are many nice algorithms for doing linear algebra and other applications, and of course, quantum simulation. But if we can manage to get quantum computers to do machine learning, that is to take data from the outside world and to process it in a uniquely quantum mechanical fashion, then we have quantum computers have the potential to do much, much more than they can do with the other algorithms, because so many applications of computation these days are based on machine learning. And so I'm in this talk, and Casey, how much time do I have for the talk? What is the schedule?
We have about an hour, including questions.
Okay, good. That's what I was planning on. I just want to make sure. So I'm going to describe what are the potential applications of quantum machine learning right now, and there may be many more applications. I'll give a review of the field and why we think that quantum computers might be good at providing speedups, indeed exponential speedups for the analysis of data. And then I'll describe the various barriers and the issues involved in trying to make it actually work in practice. The primary issue, just to say what the primary issue is how do you load large amounts of classical data onto a small quantum computer? That is a big issue, and I'm going to spend a bunch of time at the end of the talk talking about why I think it's promising that we may be able to actually make this happen. And again, just to say how this might work, here is a picture here, which you can see, and here we have on the right we have a happy little quantum computer, and in order to get large amounts of data, for instance, pictures of cats and dogs, if we wish to say distinguish between cats and dogs, we need somehow to map this classical data, which involves typically a large number of classical bits, into a much smaller number of quantum bits, and to construct quantum states that represent the classical data, which we can then use. Once we constructed quantum states that represent the classical data, we can then process this using the power of quantum computers to do linear algebra. And so here's a classical computer. It's like a Turing machine. This is what computers looked like when I was learning to program back in the 1970s, if you can imagine. They had like tape drives and like paper tape readers and things like that. Now, so that's what the talk is going to be about. And I'm going to request that people ask questions while I give the talk. And I'm going to stop at various places and then ask people if they have questions. But at any point, please put a question into the chat, and I'll monitor the chat while I'm giving the talk, and then I'll try to answer the questions as they come along. This is because it's much better that you ask questions if you don't understand something or you want further clarification, then you should ask right away, and I'll address your question. Is that clear? Does anybody have any questions they'd like to ask right now? Any topics they'd like me to cover? If so, just put it in the chat right now. I'll see it when it comes up. Okay, I see nobody asking any questions, so let's actually go to the next slide. So now what is the motivation here? The motivation is that quantum computers can perform linear algebra exponentially faster than classical computers for a wide variety of problems that involve sparse and low-ranked matrices. And these problems are very common in machine learning. Now, the second motivation for looking at quantum machine learning is that quantum systems can generate patterns of data that classical systems can't. I mean, this has been known really for almost 100 years since the discovery of entanglement and the subsequent exploration of Bell's inequalities. And so we know that quantum computers can generate patterns that is hard for classical computers to generate, or classical systems to generate. And so if we turn this around, in machine learning, we often see that machine learning systems like deep neural networks can be trained to recognize patterns, and they can also be trained to generate patterns. And if a system can generate a particular pattern, it typically can recognize that type of pattern as well. I mean, there are famous examples of, Google training a deep neural network to recognize pictures of kittens on the internet, though actually there are so many pictures of kittens on the internet that maybe it's not so surprising that they could find these pictures of kittens. But then the same algorithm can also generate pictures that make things look like kittens. So we're going to use this duality in machine learning that of generation and recognition and apply this to quantum computation. So because quantum systems can generate patterns in data that classical systems can't generate, then it's reasonable to expect that quantum machine learning may be able to identify and classify patterns that are classically inaccessible, that classical machine learning devices cannot generate. And I'll say right now that we can definitely find such patterns, because if we actually use quantum machine learning to try to recognize patterns in quantum states, that is, the input to a quantum machine learning device is a quantum state that comes out of an experiment, for example, say a set of photons that are entangled in some funny way, then we can show relatively directly that quantum machine learning gives you an exponential advantage over classical machine learning. So we know that quantum machine learning will give us significant advantages if what we're trying to do are problems like state or process tomography for quantum systems. But there's the open question, and it's a very interesting open question, is whether quantum computers can actually find patterns in classical data, pictures of kittens, for example, that classical computers can't. So that's the end of the introduction. Are there any questions at this point? Okay.
Actually, I do have one question, if it is okay.
Yeah, absolutely.
So yeah, your second bullet point actually says that quantum system can actually generate patterns in the data that classical system cannot. So
Yeah.
that is certainly true. So all of us here are physics graduate students and postdocs. So this is certainly true. But however, actual experiments is actually performed classically. So even if it's actually the fundamental, the nature of the system is a quantum, every single measurement is done classically, and then we feed that data, obtain the classical measurements, and then into the quantum computer. But is it clear that actually the quantum effect will still exist in the quantum computer?
That's a very good question. So when I was saying what we can actually prove is that if we put quantum data into the quantum computer, that is, if we take quantum states and we say states of light, and we put these quantum states into states, we map them into these quantum states into states of qubits in the quantum computer, then we can certainly get an exponential speed up. Now, but your question is a very interesting one, and I don't know the answer to it. I mean, again, the fact that a quantum computer can model a quantum system and cloud system makes it reasonable to expect that we might be able to take the classical data generated by measurement on quantum systems and then to be able to learn things that classical computers can. but in that case, so that seems likely, I would say, but we don't have a proof that that's the case. So that's a very good problem, and indeed, because this is a like a school and the people there are graduate students, let's just like flag these problems along the way as interesting problems for research. That's a very good problem for research. So anyway, so let us let's keep that. So it's a good question, and that's a good example of asking a question, right? Because I give extra prizes for people who ask me questions I can't answer. Okay, so let's go on there. So let's just look at review what the exponential advantage of quantum computers over classical computers for performing linear algebraic methods, the basic linear algebra subroutines, the BLAS, basic linear algebra subroutines. So quite famously, the fast Fourier transform on an n-dimensional vector space classically takes time order n log n, and famously the quantum Fourier transform takes time order log n squared. Similarly, the quantum phase estimation algorithm for finding eigenvectors and eigenvalues of large sparse matrices classically takes time order n squared, and again, quantum mechanically takes time order log n squared. So, if the Hilbert space, if the vector space is n-dimensional, the number of qubits required for this Hilbert space is log n. And so typically in these quantum algorithms, the computational complexity scales as a low order polynomial in the number of qubits. That is to say, the logarithm of the dimension of the space. Similarly, inverting large sparse matrices, that takes time order n log n on a classical computer, but it takes time order log n squared on a quantum computer. A rather surprising result when Aram Haro, Avinathan Hasidim, and I came across it in 2008. And then the key point here, which I mentioned at the beginning of the talk, is the access to data. So, and this is really how all these algorithms work. If I have a vector of an n-dimensional vector that sits in random access memory, a classical n-dimensional vector, then there exists a quantum vector which I can access via quantum random access memory. And this quantum vector then takes only, if this takes order n bits, the classical one, the quantum one takes log n bits. So that's in fact, all of these speedups operate by mapping classical vectors into quantum vectors. And generically, it turns out that you can, in principle, build a piece of hardware called a quantum random access memory, or QRAM, that actually performs this mapping where it takes order n memory slots in the classical memory slot, but the mapping itself only takes resources that go as log n. However, we do not currently have large-scale quantum random access memory, and building quantum random access memory would be a very key and enabling technology for doing quantum machine learning. And I will address this question of how we might build QRAM again at the end of the talk. Yeah, so are there questions about this? Feel free to pop them in the chat or just say them. Okay. So now let's actually look, given that we have these quantum computers that have an exponential advantage for performing linear algebra, let's look at data analysis techniques and machine learning that, assuming that we actually can, again, if we can actually map classical data into quantum states, let's look at the kind of problems that we can actually do faster on a quantum computer. So one of the first algorithms we looked at is cluster finding. Here, suppose I have a set of data, and I'm told that it's supposed to sit in 3 clusters. And so my goal is to color the data, here green, red, and blue, in a way that is optimal. And a famous algorithm for doing this dating from the 1950s, is called K-means algorithm, in which you cluster the data so that each data point is identified as being in a cluster where it's closest to the mean value of that cluster. It's a very nice algorithm. And in fact, it's called Lloyd's algorithm, though it was invented by someone named Stuart Lloyd, who, so far as I know, is no relation to me. So the quantum Lloyd's algorithm gives an exponential speedup for doing this cluster finding. Then there's a famous classical method called the support vector machine, where I'm given clusters of labeled data. And here I have a cluster of data that's labeled as being red, say pictures of cats, and data that's being labeled as blue, say pictures of dogs. And the point of a support vector machine is to find the optimal separating hyperplane, or more generally hypersurface, that separates this data. And then the way a support vector machine works is that if a new piece of data comes in, say over here on the blue side of this hyperplane, then you identify it as being belonging to this blue data here. And support vector machines and related methods called, which is an example of a kernel method, which we'll talk about in a little bit, prior to the success of deep neural networks, which started just only a little more than a decade ago. Support vector machines were one of the most primarily used methods for data analysis. And as we'll see, quantum computation gives you an exponential advantage in constructing such optimal separating hyperplanes, because these are all, in fact, just linear algebraic techniques that give you an exponential speedup on a quantum computer. One of the most, in fact, perhaps the most common method for analyzing data is principal component analysis. If your data are sets of vectors in a high dimensional vector space, then you define the principal components of this data. You try to find the mean, and then you try to find the directions that are most informative, that is to say, the principal components of the data. And these are, in fact, if I construct the covariance matrix for the data, the principal components correspond to the eigenvectors of the covariance matrix with the largest eigenvalues. And so the largest eigenvalues then determine these directions of this, the principal components, the directions of where, if I tried to make an optimal oval or ovaloid that contains this data, of how you can summarize this data. There are very common methods for analyzing data are gradient descent and Newton's method. Again, these are linear algebraic methods that actually can be done exponentially faster on quantum computers. Similarly, for data fitting, if you want to make a polynomial fit to a set of data with the minimum least squares error, that gives you, by linear algebraic methods, an exponential speedup on quantum computing. And I'll also talk about a very fun method, which was developed by Paolo Zanardi, Silvano Gonarone, and me about a decade, 10 years ago. And these are recently become very popular. And these are methods for doing topological analysis of data. And just to say what happens here I have a bunch of data points, and you see that there is a hole in the middle of this data. And then the question is, how do you find a hole as a topological feature? How do you find holes in data? Holes, connected components. How do you find topological features of data? And I'll go into a little more detail on that later. And there are, if you go and look in under quantum machine learning on Google Scholar, or you could use ChatGPT, but I find it's not very reliable for this. But if you look on Google Scholar, you will find many very novel and interesting techniques for quantum machine learning. Again, almost all of them based on the ability to map large vectors of data into quantum states, potentially using quantum random access memory. Okay, Again, I encourage you to put questions into the chat as we go along, particularly questions, if you have a question and you don't know the answer to it, you can ask me. And again, if I don't know the answer to it, that will be fun for you. It's fun for me too, because I like having questions where I don't know the answer. If I do know the answer, I'll tell you. Okay, so.
Hi.
Yes, please.
Hello. Yeah, I have a question. So about this topological analysis. So, for example, I understand that if you map the data into another space using the continuous function, then this topological property can be preserved. But in the kind of this kernel method or some kind of data mapping, maybe some non-linearity can break the topological property or not. I'm not sure about this, whether this kind of data mapping can preserve the topological analysis, topological aspect or not.
Yeah, that's a really good question. So you can see that this topological analysis of data is kind of, in the way, it seems kind of strange, right? Because as you say quite correctly, topology is usually thought of as a property of continuous functions or continuous sets. And yet here we have discrete function, we have discrete set. And so how do we actually turn this discrete set into something that's like a continuous set where we can actually apply topological methods? It's a good question, and I will try to answer it when I talk about topological data analysis a few slides down. So just hold that question, and then I will try to answer it. But it's a very good question. Okay, so here is an example of how you can actually do. In this case, this is going to be doing a financial problem, which is risk management. By the way, many of these data analysis problems, including the topological data analysis problem, are very important in analysis of financial data. Financial data sets are large, and by definition, there's money involved. So people are interested in trying to analyze them. So let me give a nice example of how you can apply quantum methods to risk management. So let's suppose that we have I'll just go over the classical version of this first, and then I'll describe how it becomes quantum mechanical. So suppose we have a very large vector, R, which gives you the returns on the different stocks in the stock market. So suppose stock number 3 is Google, for example, and stock number 5 is Microsoft. And J here labels the history. So R minus 1 was the well, let's say R1 was the return yesterday. So the third component of R is Google's the fractional return of Google's stock yesterday. The fifth component of R is the fractional return on Microsoft stock yesterday. R2 is the returns the day before yesterday. R3 is the returns the day before yesterday, etc. And so R here is just the average. This is the average return over the last M days. Okay, so this is the average historical return of these stocks. So the third component of R is the historical return. If M is 100, it's the historical return of R. The third component of R is the average return over Google over the last 100 days. And the fifth component is the average return of Microsoft over the last day. Okay, now what is the covariance of the data? The covariance of the data is the linearized correlation coefficient between these stocks. So here, what we do is we take R times R transpose. So because R is a vector and R transpose, R is a column vector and R transpose is a row vector, then C is an n by n, if there are n stocks, an n by n matrix. And we average over the last 100 days. And so why is this called covariance? Well, if you look at the 3-5 component of this matrix, it's the linear correlation coefficient between the returns of Google on a particular day and the returns of Microsoft on a particular day. So it's just the covariance or, or linearized correlation between these two stocks. Now, what is the goal? Okay, we have a question in the chat. I like this. Thank you. Okay, can we embed model parameters in QRAM and use it for training? That's a very good question. I'll hold on to that, and I will keep it. I will try to answer it later when we talk about QRAM. Okay, good. So suppose we now we have our vector of wealth W. W tells us how much money we invest in a particular stock. So the third component of W is how much we invest in Google. The fifth component of W is how much we invest in Microsoft. And three, so this tells us the dot product of W with R is our expected return for given that we've invested a particular amount of our wealth, W, in each of these stocks. And then the risk for this is given by the variance of this result. And the variance is just W dagger C W. That's the expected variance in our return. And the goal here, and by the way, what I'm describing is just a very classical method dating from the 1940s and 50s called Markowitz portfolio management. It's a simplified model of portfolio management, but it gives lots of the features of it. The goal of the analysis is to find the optimal risk return curve. So here is this green point is a particular stock. It has a particular expected return, which is the value over on the vertical axis. And as a particular risk, which is the variance, which is its value over on this axis. And then what you'd like to do is for a particular return, you'd like to minimize the risk. Or for a particular risk, you'd like to maximize the return. So here you see this green stock has a particular risk, a particular variance in the return, but it doesn't maximize the return. So what we'd like, if I fix the risk, I'd like to find the portfolio that maximizes the return. You might say, hey, we'll just try to maximize the return, but in general, trying to maximize the average return gives you a very, very, very high risk. So these stocks portfolios out here that give you higher average return have a very high risk. So your goal is to say, well, I'm willing to take this much risk. If I want to take this much risk, what's the amount of maximal return I can get? Or if I want a particular return, how do I minimize the risk? Okay, so we want our optimal portfolios are portfolios on this curve right here. And then actually here you can just set this up as a Lagrangian optimization problem. Here's this Lagrangian L. We want to maximize the expected return. We put a constraint on the risk. We try to solve this problem. We find that the solution goes that C, the covariance matrix, times the optimal portfolio is equal to 1 over this Lagrange multiplier lambda times R. And then this is just a matrix inversion problem. And so when we turn this into a quantum problem, we map all our vectors R into quantum states. Our covariance matrix is now just the density matrix for these states, because you see very nicely that the form of the covariance matrix, it just ends up being the density matrix for these states that we have. And so we can actually effectively construct this matrix by sampling from these quantum states. And then we just use quantum matrix inversion, the quantum linear systems algorithm, to solve this equation. And then we can sample from the optimal portfolio. And because of the exponential advantage of linear algebra, then we actually do much better than we can classically. Okay, are there questions about this? This is just kind of a straight up application of quantum methods to using the exponential enhancements of quantum linear algebra in linear algebraic algorithms to get you an exponential speed up for a machine learning method. I'll just mention now, I'm not going to talk about this, but for these kinds of problems, then there's always the potential to use so-called quantum inspired methods to actually try to make classical versions that actually emulate what's going on in the quantum method. And so in something like this risk management, it may be possible to actually use a quantum inspired algorithm to in fact do the same kind of process, though typically with a significant polynomial slowdown over the quantum algorithm.
I have a question.
Okay.
So here,
Yeah.
if I have the 100 stock companies, 100 company for the this my portfolio, then how many qubit that usually require for this analysis? Do I need 100 qubit if I have 100 company in my portfolio?
No, no. So if you let's say do it for, because 1,000 is 2 to the 10th. So, or 2 to the 10th is 1,024. So suppose we have 1,000 companies. So each vector R then requires 10 qubits, right? And then you have you then actually have a window of how many days you have. So then you want to have you need to average together this R over the number of days that you have. Actually, you can use sneaky tricks. So you might think you need to have like 10 times the number of days, but in fact, you can actually, if your information is in QRAM, then you can construct this vector R and you can sample from this vector C using only on the order of 10 qubits. So it's a very small number of qubits. If you have 1 million stocks, then you need 20 qubits. But you need a QRAM to be able to load this information into this. And then the matrix inversion will take on the order of a few hundred steps for on a quantum computer. So you see, you're classically, you have to invert 1 million by 1 million matrix. Quantum mechanically, you're inverting 1 million by 1 million matrix. Classically, that takes quite a long time. It could take like, 10 to the 12 steps to invert a million low rank matrix. But quantum mechanically, it only takes on the order of, because we're only using around 20 qubits, it will take around, 400 or 1,000 steps on a quantum computer. That's just to give you an example of how this exponential speedup works. Okay, so again, keep on asking the questions. I'm happy to answer them. These are all great questions. So now let's look at another method, that of quantum generative adversarial networks. Generative adversarial networks are a very common and nice technique in classical machine learning. And rather than describing how the classical method works, I'll just go directly to describing the quantum method. Because actually it's just, very close to the classical method. So suppose we have real data, and the real data has a particular distribution, or in our case, version is described density matrix rho. So we have some source of this real data, and it's described by density matrix rho. And then we have a generator. Here it's being represented by Bob, who's trying to generate fake data. And Bob's goal is to generate data that actually mimics the real data. So Bob's generating quantum states described by a density matrix sigma. And then over here is Alice, who's called the discriminator, and she's given either a sample from the real data or a sample from the fake data, and she doesn't know which it is. So Alice's goal is to try to perform a measurement that optimally discriminates between the real data rho and the fake data sigma. So it's an adversarial game in which, and the way it works is they take turns. So Bob will generate fake data with density matrix sigma. There's the real data with density matrix rho, and then Alice will try to improve her measurements to do better and better and better. So for a fixed, and then Alice fixes that measurement, and then Bob tries to fool Alice. So let's look at the steps. So first, there's the real data rho. Bob is generating fake data with a density matrix sigma. And Alice's goal is to choose an M, a positive operator valued measurement. It's just a positive operator with norm less than or equal to 1. to maximize the probability of figuring out that the data is real or fake. So she actually wants to maximize trace rho m rho minus trace m sigma. This is the probability. Trace m rho is the probability she gets that she identifies rho correctly. Trace m sigma is the probability that she incorrectly identifies sigma as being the real data. So she needs to actually find this m. Note, however, that this is a convex problem because the space of positive operators with norm 1 is a convex set. So actually, this is not a hard, in some sense, not a hard problem. If she has access to different ways of generating different measurements, then it's a convex problem to try to find the optimal. And then Bob's role is to maximize once adversarial gain. In this adversarial game going back and forth, then we find that there's a unique Nash equilibrium to this game in which Bob ends up fooling Alice, in which Bob is generating data with the same statistics as the real data. And this is an example of a problem that, as I mentioned before, where we can, it's straightforward to see that in the quantum context, that if Alice is actually trying to make quantum measurements on real data that's being produced by a quantum system, and Bob is producing, quantum states, these fake quantum states, that this process for a quantum, if they were actually analyzing quantum data, then a quantum generative adversarial network is exponentially faster than any classical method could actually be. Okay, so ask questions. Any questions about this? All right, let me go on then. So here's this a method that we call deep quantum learning. It's an example of a kernel method or support vector machine as before. Here the goal is you take quantum states and then you produce, you might want to actually optimize, you send these through a quantum circuit with parameters theta, and then you want to optimize the theta to make a unitary that's as close as possible to a particular unitary. Of course, it's a generic variational quantum circuit. And so variational quantum learning tries to learn quantum circuits that will actually have particular properties. For example, in this case, to try to learn a particular unitary. And there are many examples, including many experimental examples where people are using these variational quantum circuits on superconducting circuits, ion traps, using linear and nonlinear optics in order to accomplish various tasks. For example, in learning the ground states of complex quantum systems. However, here, what we want to do is we want to take classical data, these, say, 3 different types of data. They might represent dogs, cats, and let's say frogs, and because the frogs are green, dogs, cats, and frogs, and then we try to optimize the parameters of the quantum circuit that we're going to map these states into states in Hilbert space. So we're mapping the dogs over here to these x vectors, the cats over to these y vectors, and the z's over, the frogs over to these z vectors here. And then the goal, as in, if you may recall, let's go back here, quantum support vector machines, once I've actually mapped data into a particular place in Hilbert space, I try to do the optimal measurement to distinguish between them. And the nice feature about this is that if I have 3 different clouds of data in Hilbert space, we actually know what the optimal measurement is for actually distinguishing between them, because this is given by the Hellstrom optimal measurement. And there are simple quantum circuits for performing this measurement. And even simpler, we can even just use so-called pretty good measurements to distinguish between this data. And there are even simpler quantum circuits for performing this optimal measurement. And these kernel methods then are potentially very powerful because we have access to a very high dimensional Hilbert space in which to embed the data. And since this method was proposed by Maria Schold, Nathan Killeran, and myself, all working at Xanadu about maybe 5 or 6 years ago. And since then, many experiments have been performed on this, and this seems a very promising method for doing quantum machine learning. Because, and it's specifically quantum, it uses the quantum mechanical methods and access to high dimensional Hilbert spaces together with optimal measurements to be able to discriminate between clusters of data. Okay, here we go. Oh, now here is this quantum algorithm for doing topological analysis of data. I'll go over, there was a nice question about this before. So how do I take a cluster of data points, and then how do I determine whether there are holes in it? I mean, if you look at it, it looks like it's all holes to begin with. Well, the idea is that for these, and by the way, I'm describing about the classical methods first. The quantum algorithms give an apparently exponential speed up over the classical methods. And the idea is to identify holes and voids in the data, and then also connect the components via a method called persistent homology. The classical algorithms take time order 2 to the 2n, where n is the number of data points, and the quantum algorithms take time order n cubed, where n is the number of data points. And you can see how this method works. What I do is I take this data and I connect nearby data points to form a simplicial complex. I've done it in 2 dimensions where I connect the data using triangles, but it can be done in arbitrarily high dimensions. In 3 dimensions, you construct tetrahedra. In 4 dimensions, you construct 4-dimensional versions of tetrahedra or 4 simplices, etc. And you can identify arbitrarily high dimensional features of your data by this form of mapping. And so let me actually show you a little bit. Oh, sorry, actually, no, I think I noticed I did not show how it's done, but I will describe it. So what you do is you perform a simplicial complex that represents the data, and then use methods of algebraic topology to invert a very high dimensional, a 2 to the n by 2 to the n dimensional matrix called the combinatorial Laplacian. It's a high dimensional sparse matrix, and you can invert it using the quantum linear systems algorithm. And actually, I would describe it more, but in the interest of time, I think I better go on into terms of talking about data analysis. You'll find in the last year, there have been about a dozen papers written on this with all kinds of nice features and improvements on our original 2014 quantum algorithm on this topic. Okay. I'm not seeing questions in the chat, so I think I'll just go forward here and look at how you might build quantum random access memory. So QRAM, how does it work? So this is a method for loading classical information onto quantum computers. And so let's look at how random access memory works. Well, random access memory works by having a branching tree that acts data, and you have a treetional tree. In actual physical classical random access memory, you have 2 of these trees, but because that would be harder to draw and explain, I'm just going to use one of them. So here is a tree. It has 3 layers. There are 8 data entries. I only drew it that way because otherwise it would get too big to draw. And so each data point here, D101, 101, that's D, 5 in binary, has a unique entry that says, oh, okay, 101 identifies the 5th entry in this tree. And so we want to open up a path that only gives us access to this 5th entry in this tree. And this is essentially how classical random access memory works. But the way that quantum random access memory works is you want to access the data in quantum superposition. So how does that work? So if classically I just have one memory label, here's 101 or 5, and that allows me to access the 5th entry of this data point in classical random access memory. In QRAM, the idea is that we want to be able to have a quantum superposition of different entries. So here I've written, here if D is 8 in this case, but of course, if you have 10 bits of referring to the entry, you have 1,024 different possible entries. If you have 20 bits, you have 1,000,000 entries. If you have 30 bits, you have 1,000,000,000 entries. So the size of the memory can grow very large, even with a small number of qubits to access the memory. And the idea here is if you put in a quantum superposition of possible data points in the memory, then what you get out is a quantum superposition of the memory labels together with the states that represent the data in that memory point. And the neat thing about this is that this is a method that was proposed by Vittorio Giovanetti, Lorenzo Maccone, and me, back in 2008 or so. And then initial experiments were performed by Fabio Scarino at University of Roma La Sapienza around in 2009 and 2010. Since then, there have been multiple designs for QRAM, and now the experiments are going ahead to try to construct much larger sized QRAM. If you can do this, then all of the techniques we've been talking about before become accessible to quantum machine learning. All of these techniques, topological analysis of data, deep quantum learning and kernel methods, quantum generative adversarial method networks, these kinds of principal component analysis, risk management techniques, all of these techniques become accessible for quantum machine learning. So developing large-scale QRAM should be an important goal for our field in order to try to make these methods work. There's a neat feature about QRAM is that you can build, even though the QRAM itself requires a large number of switches, you can make each one is repeated many, many different times. And then the switches have to operate in quantum superposition. And the nice feature about this is that if you look at the error rate that is tolerated, so the error rate per switch there, we find that we can tolerate error rates that go as 1 over the log of the dimension here, which is, that is to say 1 over the number of qubits that are used in the memory axis there. So that's nice because we can build a QRAM that has a very large number of switches in it, but because the depth of this tree is small, then we can actually, in principle, construct QRAM that does not require high amounts of, does not require full-blown quantum error correction, which is good because full-blown quantum error correction is hard. It's hard for building large-scale quantum computers, and it's nice that we do not necessarily require it for for problems such as quantum machine learning. So, for example, if we had a tree that was 100 qubits deep, or 100 bits deep, there are 2 to the 100th different possible entries here, but it only requires 100 qubits of memory access. And that's a large number because 100 qubits is around 10 to the 30. And 10 to the 30 is a number that's much larger than the amount of data that's been generated by the entire human species in the course of its existence. So this QRAM is potentially very promising, but it is still not easy. It's a task that is on the same order of difficulty as constructing fault-tolerant quantum computers. Possibly easier because it itself does not require fault tolerance. So now that's a hard problem, but it's one that's worth pursuing, and many people are out there pursuing this, trying to build QRAM right now. So let's now look at easier ways of doing this. So my claim is that we can actually load quite large amounts of classical information onto quantum information processors just right now without doing anything particularly special. And for this, we'll look at superconducting systems, we'll look at ion traps, and we'll look at spins in solid state. We'll find out that spins in solid state and ion traps have very similar kinds of figures of merit. So these systems have different bandwidths for addressing the qubits. The bandwidth of superconducting systems is of the order of 10 gigahertz. For ion traps is around 100 megahertz. For spins in solid states, it's about 10 gigahertz again. And then we'll look at the coherence time and the interaction strength of these systems. And we'll look at we can see that there is a very simple formula that tells us how much information we can put into these systems. So by the way, this is just really a back of the envelope calculation. We're just asking, if we address these systems over a period of the coherence time, then how many classical bits of information can we load onto a quantum computer or quantum information processor in the course of the coherence time? So here we have the important number here is the bandwidth times the coherence time. This is the number of samples, the number of bits in a classical signal with particular bandwidth that this classical signal effectively contains. This is just classical Shannon theory. And that number is essentially the number of samples, which we sample the system at the Nyquist frequency, that is to say the bandwidth of the signal, and how many classical samples we can put in there, number of bits per sample, and then suppose that we can address each of the qubits in our quantum computer at that rate. So here's our formula right here. Here, look at the coherence time. So the coherence time of superconducting quantum systems is pushing up to a millisecond. For ion traps, the coherence time is seconds or even many seconds, actually. And spins in solid state is also around 10 to the minus 3 seconds. So if we go and just use this very simple formula and ask how many bits, classical bits, we can load into our current systems in the coherence time, we find something that rather nice. That is, if we look at the solid state systems, such as we have 100 qubits, 10 bits per sample, and we look at the amount of classical bits we can load into a quantum state, then we can load around 10 to the 10th bits. That is to see that something that corresponds to 33 qubits. We can load in a gigabit, 10 gigabits of information onto a superconducting system with 100 qubits in its coherence time. For atoms and ions, the time is even longer. Here we can load on the order of terabits of information, 10 to the 12th bits of information, corresponding to about 40 can put in. And this actually, because this is quite, we're putting into classical information we can put in our quantum systems. Moreover, these then become the amounts in where we can use conventional, just existing quantum computers on, say, 40 qubits or 33 qubits, and then do things on phasization, like the kinds of problems that could be solved essentially today. So this makes me optimistic that we can actually perform quantum computation and quantum machine learning on existing devices, because the algorithms that we have and our ability to load classical information match what we have right now, even without fault tolerance. So even without building fault-tolerant quantum computers, which is a very long-scale project, my guess it's going to take at least a decade. It might even be, I would say, 10 years plus or minus never. Might even be proved too hard to do. But right now, we can actually do today. And the way to do this that I would suggest, this is the method for our quantum computing company, Turing, is that we train classical deep neural networks. We're putting pictures of cats and dogs into classical deep learning networks. And we use these to, we train these to vary the control fields we're using in order to take our quantum computers and to map classical states, large amounts of classical data onto high dimensional states in our quantum computers. And this is a nice way to do this. A method again that people are using in order to try to train classical neural networks to control quantum computers. I suggest that the suggestion here is that we co-train our classical and quantum computers, where we use the power of classical AI to generate ways of controlling quantum computers to construct the states that we need to use in order to perform quantum machine learning. And this is a great project. And again, this is something that if we can do it, and we can make it work, then we can actually use quantum computers, including near-term quantum computers, in order to do quantum machine learning on large classical data sets. And I now have 5 minutes left, and I suggest that we use this for questions, if that was the last slide of my talk. So thank you very much.